Welcome everyone to our third day of the NOAA AI workshop. And if I remember correctly, this should be Plenary 5. I think my coffee is still working. So welcome to this plenary session. And we have the great honor to have a distinguished speaker to speak about AI for ocean science. Before we get into the exciting presentation, I want to remind everyone about the code of conduct and etiquette. So we want to make sure this workshop is productive, safe, inclusive, and welcoming. So if you experience any unacceptable behavior, please let the organizing team know at ai.workshop@noaa.gov or find us on the Slack channel. And with that, I want to turn the stage to Greg Dusek, who is the co-chair of the NOAA AI Executive Committee, and to chair the session.
Thank you, Douglas, and thank you everyone for joining us for the plenary on AI and ocean science. And being an oceanographer and also a member of the National Ocean Service, I was very excited to see this plenary talk highlighted, and I think it's going to be really interesting. I'm going to introduce you to the speaker, Dr. Laure Zanna. Laure is a professor in mathematics and atmosphere and ocean science at the Courant Institute at New York University. Her research focuses on the dynamics of the climate system, and the main emphasis of her work is to study the influence of the ocean on local and global scales. Prior to NYU, she was a faculty member at the University of Oxford until 2019 and obtained her PhD in 2009 in climate dynamics from Harvard University. She was the recipient of the 2020 Nicholas P. Fofonoff Award from the American Meteorological Society for exceptional creativity in the development and the application of new concepts in ocean and climate dynamics. She's the lead principal investigator of the NSF-NOAA Climate Process Team on ocean transport and eddy energy, and M-squared lines, which is multi-scale machine learning and coupled Earth system modeling, an international effort to improve climate models with scientific machine learning. She currently serves as the editor for the Journal of Climate, a member on the International CLIVAR Ocean Model Development Panel, and on the CESM Advisory Board. So without further ado, Laure, go ahead and take it away.
Okay, thank you very much for the invitation. Thanks everybody for joining in. Great pleasure to be at this workshop. It's been a fantastic week so far. I've learned a lot, and seeing the community come together, discussing how AI in the environmental sciences can, help the field move forward has been really tremendous, and it's been a great privilege to hear many of the talks in the past few days. So I'm going to give you a little bit of a, a very biased, I guess, and subjective overview of, how AI can help in ocean sciences. And of course, as scientists, we have our own, areas of research that we try to push forward, where we believe that there are some key challenges that are remaining, or some key barriers that we try to push forward. So I'm going to try to give you a little bit of a flavor of some areas where I feel AI could really push the boundaries. On the other hand, this is not going to be all the areas where I believe AI could help, but at least a few of them. And so as mentioned, so we're very privileged to have the support of Schmidt Futures on this new project, M-squared lines, which uses scientific machine learning to improve climate models and the representation of processes that are not resolved in the current generation of climate models. And so I'm going to talk about that towards part of the talk. So I'm going to start with a little bit of, why AI for ocean sciences. So, some of the answers are going to be pretty trivial, and some are a little bit personal. I'll tell you a little bit of my story on how did I start working with machine learning for the most part several years ago, and why I continue working on this. And I'm going to touch on a few key areas as examples where, AI for ocean science could help us. And as I said before, it's very subjective, and it's definitely an incomplete list. So I'll talk about speeding up computations, or part of the computation. Talk about spatial temporal reconstruction. So basically kind of improving the data that we have and being able to actually learn something from the data that we have. Forecast and predictions, and especially rare events. And we've seen a lot of talks this week in this area, of course, from sub-seasonal to seasonal and even longer. So we've seen a lot of talks in this area. Then I'm going to focus on my own area of expertise, which is how can AI help us extract more accurate representation of small-scale processes that cannot be resolved in ocean and climate models? And that problem has been around for many years, and it's going to be around for decades to come, because it doesn't really matter how much we keep increasing the resolution. There's still many processes that we don't resolve, or many processes for which increasing resolution doesn't do anything because we don't have any governing equations for it. I think here AI can potentially help us break some of the former barriers. And I'll end with some thoughts, again, which will be very personal and my own, on where the field or where as a community we might want to move forward. Okay, so let's start with the basic question. Why AI for ocean sciences? So I'm afraid I don't need to say much here, right? So the planet has been warming. A lot of the excess energy that we have accumulated in the climate system by burning fossil fuel has been accumulated in the ocean. So here, this movie is basically the passive uptake of ocean heat, so the excess heat that ends up in the ocean under climate change. And what we can see is, of course, the planet has been warming over time. So we're getting towards the present, and we see more and more heat being accumulating in the ocean. So about more than 90% of the excess energy ends up in the ocean. As a result, water expands, sea level goes up. And again, we've been seeing rising sea levels pretty much everywhere. And that puts our coastal community at risk as global mean sea level goes up. But it doesn't go up everywhere in the same way. And of course, we're also affected by storms and extreme events. And again, unfortunately, I don't need to remind us of the recent floodings, both on the East Coast and pretty much everywhere around the world. So as our planet is warming, the ocean is a key component in, again, absorbing that excess energy, which means that it delays the surface warming, nonetheless means that sea level goes up, and it keeps basically fueling some of the storms that we see around the planet. So my personal journey into ocean dynamics and then into AI kind of started with a PhD, as mentioned, in 2009, and I was trained as a climate dynamicist. So I was trained in basic understanding of equations and how the ocean works and how we can write equations and how we can come up with simple theories and GCMs for it. And then slowly, I felt that there was a lot of data that we were not using. So can we actually do anything with that data? Try to understand how the ocean has been changing. And so started dabbling towards the end of my PhD and saying, okay, let's try to come up with some basic statistical model of, say, sea surface temperatures. Can we predict them? Can we predict them on longer time scale than what people have been using generally when they did data-driven prediction? So we're really thinking about kind of decadal predictions of SST from data, and kept doing that back and forth between, okay, we have data and it's great, but am I learning the right physics out of it? And during my PhD, I did a lot of modeling and theory, but then I was left in this kind of hypothetical world where I did not connect it to the data. And I found that the models were always stuck to a certain point. There are many missing processes, and they affect the dynamics, and so that means that they affect our ability to predict the future. So kind of started moving into combining all those kind of ideas. Can we actually start thinking about improving our models with data and learning better representation of processes? And so early on, we started by doing things, if you want, by hand, and trying to learn new parameterization of turbulence. So basically new representation of turbulent processes in climate models, just based on data and physics. And then, of course, in parallel, and much faster than my own personal development as a climate scientist, massive changes, of course, were happening in the machine learning world or in the AI world, where more complicated architecture were being developed. They were faster. They were able to actually capture different phenomena in a way that never thought was possible. And so, slowly, my thinking was, okay, so we have a lot of new tools and it's exciting. There's a lot of data. I still like dynamics, so let's try it out, right? So let's try to actually play with machine learning for parameterization. And I was lucky to start with a student in 2016. And so it was very, very early on, for the world, at least, of closures and things like this, of using ML. So we had absolutely no idea if that was possible. And, as I mentioned earlier, now we're really in this kind of world where we're actually going to try it out for many processes in climate model to try to improve them. So really kind of pushing the boundaries of using ML for those representation parameterization. But when I started, right, so if we look at the number of publications that has the word AI plus ocean or AI plus climate, it was kind of 2016. So it was kind of, going up. but it's been going up exponentially over time, right? So really, we're in this era where the explosions of papers and ideas of merging machine learning, ocean, and climate science has definitely went beyond anything I actually thought was possible. And so that makes it pretty exciting, but also gives us some challenges. So I kind of wanted to give you an idea from where I come from, and I think it will explain also some of my thought process as we move forward. Okay, so why AI? Increase in computing power, and that has been really kind of the key revolution for the machine learning world. But for us, in environmental science or in ocean sciences, also the increased data volume and the quality of data that we're getting. So, I really like those kind of, plot down here. So what you can see is kind of the, what they call the data tsunami, where, for the ocean, we see more and more data. So, we started with simple bottle and sample water earlier in the 20th century, and then move with more complicated, like, buoys and algo drifters and so on and so forth. So again, massive amount of new data coming in, sampling more and more of the oceans. Of course, a huge sway of satellite data, so giving us really a nice picture of what the surface ocean look like, whether it, how the sea level moves up and down, how the surface temperature of the planet and the ocean has been changing, giving us, some ideas of those kind of nice turbulent structure that can mix and steer different properties in the ocean. But also model data is going up, right? So this is kind of the growth of the NOAA archive as a function of time. And of course, it's prediction over time. You can see that, the data sets are going up, both for the real data, but also for model data is going up. And so again, we have more, simulations, we have more computing power. And so we generate a lot and lots of data of huge, diversity, if you want, in a sense. And so this is really what has been changing, I believe, and kind of gave us this kind of exponential rise in using machine learning and AI for ocean sciences. So we try to kind of poke at a few areas where I think, there are some low-hanging fruits and some areas where I think we're still going to need to scratch our head for quite some time to come to actually see any fruition, or if we actually did a good job or not. So speeding up computation, this is almost, kind of one of the, if you want, the reasons that the AI and AI in general and AI in the physical sciences started is you can actually make computations faster, and we can use them because we have faster computation. So when we run a coupled climate model and Earth system model, there are several parts of those simulators that are extremely expensive to run. And so one example in the ocean is the biogeochemistry. So we're talking about basically, moving around different type of tracers in the ocean. So it's a full three-dimensional, ocean, has timescale of adjustments that are hundreds or thousands of years. And we have a lot of tracers in the ocean, a lot of biogeochemical tracers are absolutely critical for, understanding the planet and predicting what's going to happen. And so here's a recent paper that tried to actually use deep learning to come up with an emulator for the biogeochemistry. And actually many other components, but I'm just going to focus on the biogeochemistry. So here's the original simulation of a biogeochemical tracer that they're trying to reproduce. And this is the emulator that is only driven with data. So really kind of going at it with a deep neural network architecture that tries to simulate or tries to emulate this kind of full simulation that solves a lot of different partial differential equation discretized on the grid. That's the relative deviation between the two. And you can see that it does a really, really good job. But what's more interesting is the simulation speed up, right? So if you want to emulate something, so you want to do a good job at it, but you also want it to be computationally efficient, right? It's kind of the main point of the emulator. And here it's about, so for this MOPS, which is again a biogeochemistry model, I didn't say it, but they end up with something that is basically about 10 to the 9, speed up. So basically about 1 billion times faster overall to actually run this data-driven architecture rather than solving the full PD. So it's really impressive, right? So if you find the right architecture, find a good emulator, you could actually speed up quite massively those very time-consuming integration in the model. And so that is, a pretty good approach, right? It's a pretty good approach and could be very exciting, but of course, those emulators need to work under different conditions and under different climates for us to be able to trust them. But nonetheless, speeding up computation, I believe, is really one key aspect where ML could work or AI could work. Another one is, the problem of oceanography in general is the ocean is big, right? It's a three-dimensional, ocean, covers 70% of the planet. And if we go back in time, there are many places that were not sampled. Even today, even though we have more buoys, more data, there's still many places that are sparsely sampled. The data is noisy. If you go at depth, there is a lot less data. And so here is just kind of give you an idea of the number of profiles, over the 20th century, and then at the beginning of Argo, basically, where we had very few data points earlier in the 20th century. In the 50s, a lot of ship of opportunities and a lot of tracking all over the place, but still the 50s, right? So a fair portion of the ocean is actually not sampled at all. Today, again, we cover much bigger portion of the ocean, but there are still many places like the deep ocean that are poorly sampled. So how can you actually fill in the gaps, right? And so that's been a problem in climate science for many years. How can we close the energy budget? We know a lot of the energy ends up in the ocean, so we need to be able to understand and quantify that better. Gives us a first indication on how to predict what might happen in the future, or how to constrain predictions. And so, many people have tried to come up with reconstruction of ocean heat content and other properties. And so here, one example that came out pretty recently is how to use neural net to really try to fill in the gaps if you want. And so here is just an example of ocean heat content, full depth, and I think we can concentrate on that, that has some error quantification around it to some extent, that tries to actually reproduce or fill in the gaps on how much the ocean has been warming over time, and giving us a kind of a better understanding of how the planet has warmed and what might happen in the future if we use that as a constraint. So that's another area where I think using optimally interpolating between data, whether it's spatially or in time, might be something that ML can really push the boundary. Another area which we've heard a lot about actually during this workshop is prediction or forecasting, right? And so again, in oceanography, one of the key aspects that we try to understand is sea level. And sea level extremes, again, have definitely been consuming our thoughts these days, because climate models struggle a little bit because of their coarse resolution. So we do have a lot of regional models, and there are a lot of models that are used to make regional predictions, but it can be pretty costly. And of course, the question is, can we actually find a way to make that cheaper and to potentially make them more useful or more efficient, or find a different way to improve on those extreme predictions? So here's another paper that came out recently that tries to actually use neural networks, again, as an ensemble, to predict extreme events in coastal sea level. So here's just a couple of time series. So anomalies in sea level as a function of time. And what we see is basically the black line. I see a different color on my screen suddenly. A black line that is kind of the surge as observed. Then different systems or benchmark, but we can just compare it with the neural net, which is this kind of red curve over here. So it does a pretty good job at predicting extreme events with a certain quantification of uncertainty. So now, of course, like any machine learning model that I've been telling you so far, in the past 3 examples, you need data. You need good data to start with if you want to emulate something, or if you want to predict. And so the question always arises: do we have enough data to actually make use of those of that data set and use machine learning to be able to predict those events? And is the data sets that we have now can help us predict what might happen in the future while the climate system continues changing, continue evolving? So those are very much open questions that we need to keep in mind as we use machine learning in general. But I feel, again, as we're getting more data, more diverse data, higher frequency, both in space and time, those are questions that we can explore. And I think we've seen many examples of that, especially in the atmosphere, on how we can use those data sets to improve prediction, and especially extreme event predictions. So now we're going to move into the last area of research where I feel AI could help, but this might take us a longer time to actually figure out, if you will. And so this is improving the representation of end-result processes in climate simulation. So here I'm showing you a suite of 3 different climate model, and we're looking at temperature. So it's the same coupled climate model. It's the GFDL CM2 suite. And we're looking at the temperature field when the coupled climate model is run at 10 kilometer resolution. So basically about 1/10 of a degree, 40 kilometer resolution, and the typical climate model type resolution, which is about 100 kilometers or so. So of course, what you can see is the field becomes blurrier, which is to be expected because you have less resolution, when you have a coarser grid. But what's most important is that a lot of that turbulence that we're not resolving in those kind of coarse resolution simulation are absolutely critical in steering and mixing tracers. They're critical for heat uptake, carbon uptake, oxygen, and many other things that we care about, both in the ocean and for the climate system. So I'll skip that one. So what we've been kind of trying to think about for many years in climate modeling is how to actually come up with representation for all those small scale processes in coarse resolution climate model. And so what are those processes, right? So in the ocean, I talked about turbulence, so all those eddies that can steer and mix, clouds, gravity waves in the atmosphere, interaction between the ice and the ocean. So all those processes are too small to be resolved on a typical climate model grid. So what we've been doing for many years has been trying to come up with mathematical representation of those processes. Idealized mathematical model, they're going to try to capture the effect of those processes on the large scale view, right? So it's a bit different than what traditionally people do in machine learning, which could be like super resolution or something like this. Here in the closure problem or in the parametrization problem, we're really trying to find a mathematical expression or some kind of functional form that depends on the large scale flow. And what we're going to do is we're going to then take those idealized representations, the idealized mathematical model, and we plug them in the coarse resolution climate model that we had and basically forward that in time. And hoping that we've improved our climate simulation at coarse resolution compared to the high resolution one. So we have 2 steps here. First, learning a representation that typically has been done by using, kind of empirical physical principles and finding the best mathematical model for it. And it's been, it's improved climate model quite drastically, but we still reach a point where there were no more improvement. And yet we have many processes in the ocean, like in vertical mixing, eddies in the ocean interior, or those in the mixed layer that help re-stratify the ocean and take up heat, are still being parameterized, and there's still a long way to go to improve them. So our main idea was, okay, can we leverage ML and all those data sets, both from numerical simulation and potentially observation at some point, to learn a representation of those small scale processes? So I'm going to show you a few examples for the ocean. And so what we've done is basically use the input of high resolution simulation that we filtered and kind of trying to make it as bad as what a coarse resolution model should look like, and trying to learn what's missing from those blurred coarse resolution models that we want to learn from. And so what we've done is, so we took those kind of coarse resolution velocity diagnosed from the high resolution run, and we use neural nets. So convolutional neural nets, because they've been extremely good at extracting information from images. And we try to learn, basically optimize for a missing forcing. So this kind of missing forcing, this missing closure that is basically the impact of the turbulence on the large scale flow by using neural nets. So, you always have a loss function. So I'll go to it in a second. We have a loss function, and we're trying to make a prediction by minimizing the loss function given the truth, which is the diagnosed mixing forcing directly from a high resolution simulation that we've caused by. And so what the neural net is going to give us is going to be basically a rather convoluted, if you want, function of the velocities in our case that we would want to plug into a coarse resolution ocean model. Okay, so I'm going to show you a few results kind of briefly. So we've played with a range of different input and outputs. And here's one of them where we use actually data from a global climate model that we again filtered and coarse grained and took the velocity field from that realistic climate simulation, and learn in this case a probabilistic parameterization. So what do I mean by that? rather than learning this missing forcing as, oh, I have a given input, which are the velocity, and I'm getting a given output, which is the missing forcing that I need to put in a coarse resolution climate model, we decided to learn a probability. So we're going to learn the mean of this missing forcing and its standard deviation. So that gives us a bit of a quantification of uncertainty, if you want, in this closure, in this parameterization that we're looking for. So this is what this kind of little cartoon looks like. We take the surface velocity as input, we pass them through this CNN, this convolutional neural network, to learn basically the first two moments of a probability distribution function for the missing forcing that we want to put in a climate model at coarser resolution. Just to show you a little bit some example, so we basically train on a PI control simulation, so where the CO2 is at the level of pre-industrial, and this is the R square. So basically it tells us how good we're doing. And so, in a few regions where it's blue, that means we're doing poorly, and that's usually the high latitude where it's covered in ice. So that's not hugely surprising because we've been trying to learn ocean turbulence. So it does poorly in regions where actually it's covered in ice. But pretty much everywhere else, we get at least 70% skill in learning this kind of missing force. So we try another test. We said, okay, let's try not to retrain the parameterization and just validate it. And test it, against a simulation in which the CO2 is double what the PI control was. But we're not retraining, we're just checking if we actually learn the turbulent forcing that would be useful if we were making predictions in a warming world. And so here you can barely see a difference. To be honest, actually it looks a little bit better. So when we actually test against the 1% CO2 without retraining, our learned subgrid forcing does a great job. So learning from PI can transfer and generalize really well to other climates and actually other regions as well. So those neural nets are really good, right? So it's not hugely surprising because they apply to other, to other tasks. And turbulence seems to be a lot of features that can be well captured by the neural nets. Another, plus of this approach of learning a probability is that you get a confidence interval when you want to, look at your prediction. So this is the prediction of the forcing as a function of time at a given point in a Gulf Stream where it's very turbulent and there's a lot of activity. So the prediction is the orange line that you see here, compared to the truth, which is the blue. And the green one is basically the confidence interval that we calculated from our standard deviation. So again, what you can see is that this uncertainty helps us encompass places where the simple mean would not have done a good job, especially where we have extreme events. But it's standard deviation, the fact that we have some uncertainty quantification around it, actually help us capture those extreme events. So we're thinking the way we actually train those neural networks and the way we're thinking about the output is definitely something that we have to think about when we build parameterization. And that applies to pretty much any prediction problem that we've seen so far, not just the parameterization. Okay, so far I showed you neural nets, right? I have no idea why they do what they do. I just know they do well. So we got a little bit frustrated with that. And so we thought, well, let's try to come up with something that is a bit more interpretable, but it might not have as much skill. So try a different method here. And this one is this trying to discover equation. So we did the same kind of exercise. We took a high resolution run, we coarse grain it, we try to learn the subgrid forcing that is missing from a coarse resolution model. But in this case, rather than letting a massive neural net with thousands of parameters find the best fit, we basically give the algorithm a library of function, a library of basically derivatives of the velocities and curl and so on and so forth. And we ask it to prune through that library to come up with a closed formed equation for the parameterization. This is what we end up with. I'm not going to explain what it is, but it's something that actually relates to turbulent fluxes, and we could make sense of them. So in this case, it's still data-driven, it's still machine learning, it's not deep learning, but it gives us a better handle on how can we interpret, whatever we learn from the algorithm. And I think this is a key part as we move forward with ML and AI, and that's been, discussed many times this week. We need something that is interpretable or, explainable, or however you want to phrase it. We need something that we can have, some understanding of, so we can actually see it can generalize to different climates or different regimes. And for those kind of physics application, it's absolutely crucial. Okay, so now I told you we had one step that was learning those kind of subgrid closures from simulation. And so learning those kind of representation from machine learning. Now we need to see if it actually works when we plug them into a model. So now plugging them into a real climate model is not an easy task. And we're in the process of doing it, but we still have a long way to go. So I'm just going to show you a couple of slides with very idealized simulations. One is what we call a barotropic model. I mean, it's one layer ocean. It's a very boring ocean, but it's a great ocean theoretically. And so we try to implement all those kind of closures that I discussed. So this is kinetic energy on the y-axis as a function of time in year. So the truth, which is the high resolution, is this kind of cyan curve that you see here. So a lot of energy in that field. The gray line is the low resolution model in which there is no parameterization. So you can see there's less turbulence or less kinetic energy overall. And now what we did is we took the low resolution and then we added on our newfound closures. So one is the neural network, and one is the equation, the equation discovery, or the equation parameterization, if you want. So what we found is in both cases, they improved the simulation quite drastically. But in both cases, we had to tune. Now the tuning gets different depending on the model in which we implement the parameterization. So here I'm showing you this very idealized one where it's one layer. When we go to 2 layers, the tuning factors become different. And so that's something that we still don't understand. How should we tune it and how does it work? But nonetheless, I'll kind of go back to the positive is in all instances actually works. But there is a lot of tuning involved. And for the equation discovery, for example, the model blew up. So it became numerically unstable. While for the neural network, it started giving us unrealistic behavior. So there's still an aspect of this kind of coupling between the neural network and a forward, if you want, PDE and a forward climate model that is still missing. And that's really a key aspect that we're still stuck on. So I'm going to skip this one just, I think for a matter of time. I think I have a couple of minutes left. So we tried in a more complicated model, and I'm happy to take question on this one later on. So I'm going to try to summarize, and so there's going to be plenty of time for discussion. So first, parameterization for unresolved processes are still in demand, and they're going to be in demand for decades to come, right? So whether you're thinking about coastal oceanography or large-scale climate dynamics like I do, there are many processes that you can resolve, whether it's in the ocean, at the interface between the ocean and the atmosphere, many processes that we're going to need to parameterize. And so far, the mathematical physics approach has been useful, but we kind of got stuck at some point. We didn't improve models anymore. And there are still more and more processes that we don't resolve. And we have more and more data that we should be using to learn from. And so I show you 2 results, right? One is deep learning, high skill, highly generalizable and transferable to kind of many regimes and many models, but interpretability is pretty difficult. So we've been trying for quite some time now. I still don't know why it's doing what it's doing. And so I still like to give the cons as well of those approaches. Equation discovery, I've been having a lot of fun with it, I have to admit, because it's highly interpretable. It's a bit of a different way to think about it. You start with the data, you learn an equation, and then you need to scratch your head. Does that equation make any sense or no? Or did we just pick up any random operator? It's very cheap computationally, by the way, to implement because it's a simple mathematical operator. But I think the fun part that I see it is that it's really a way to discover new physics or biogeochemistry or any of other processes that you're interested in, and kind of have a different approach on how to use the data to come up with those ideas. For the implementation, I told you tuning is needed for numerical stability. Uncertainty quantification is still needed no matter what you do. We still, those representations are still inaccurate. So we need to have an understanding of how inaccurate they are if we want to have prediction for which, if we want to take any action with the predictions we're making, understanding where the errors come from and how certain or uncertain we are is crucial. Efficiency needs to be tested, right? If we try to actually make a computationally more efficient, that's something we need to come up with good benchmark for. And we still don't know if we're really going to improve global climate models. And so that's still in the work, and that's what M² line is all about. So really trying to go after all those processes we don't resolve in climate models, both in the ocean, in the atmosphere, at the interaction between, and the interaction between, the ice, ocean, and atmosphere, and try to improve climate models. So a shameless plug, we still have a postdoc, position open at NYU. So, if you're interested in those ideas, then please join us. It's a lot of fun. So my thoughts. I think AI is a way forward, but I think everything I showed you kind of tell us that, with a lot of the problem that we had were identical to the problem from the past. Incorporating knowledge, uncertainty quantification, model stability, computational efficiency, all of those problems have been around for decades. So there's nothing new about AI. And so that's why I feel like, combining domain knowledge with those new tools and those new techniques is absolutely critical. So it should not be physics versus data-driven. It has to be physics plus data-driven. And we've seen many talks along those ways. And, we're facing similar questions and roadblocks with AI as we faced in the past, right? I think a big question here is, we can't keep publishing and doing a lot of work, but how as a community can we, move forward? And so, we have to work across discipline, and that requires training, right? Many of us, as I showed you at the beginning, I was trained as a climate dynamicist, and I picked up tools along the way, but we need to find ways now as the field is growing and pretty much exploding, to train each other or to train the next generation to actually work together and blur those boundaries. We need to find a way to leverage those new tools and those diverse data sets and tools. And so there are many communities that are really kind of coming forward to try to push those areas, but we also need to set up rigorous benchmarks and tests, right? If each one of us, and I put myself included, we keep publishing things, but don't have good tests or benchmarks to compare against, then it's very hard to actually decide what works and what doesn't. But on the other hand, it's also a pretty great time to be, creative and, help solve some of the biggest challenge in ocean and climate science. And I'm, for one, definitely, very excited about the future of AI in ocean sciences and climate in general. So hopefully there should be plenty of time for questions. And thanks again for having me.
All right, thank you, Laure. That was excellent. A really great presentation. Really appreciate everything you covered there. It's very interesting. I want to remind people to use the Slido for questions. We have a number in there already, but look in the chat for the link, and please enter your questions and upvote questions you'd like to see Laure answer. And we have a few minutes here to do that. So I'll kind of go down the list here. The first question they ask, the oceans are changing much faster than the expertise of many marine scientists. In other sessions, there have been discussions about teaching domain experts ML/AI versus trying to get ML/AI experts up to speed on domain expertise. How do you see this challenge for the future of ocean science? And I think this is largely what you were just alluding to a little bit of this in your last slide.
Yeah, that's great. I think this is an absolutely great question, and I think this is something that we do need to think about. Again, as I said, many of us in the climate community were trained with domain expertise and are picking up the tools, while people in the ML world, had test cases that don't necessarily apply to the physical world. So I think right now what we're trying to implement is really starting from scratch, right? It's trying to develop new classes where, ML folks can actually play with, climate data sets and vice versa. So I do, for example, at NYU teach a class in ML for climate. So, we start with the basic climate and then we pick up tools as we go along. And I think this is something we really need to think about very carefully, because we need both. I don't think it can be one or the other.
Agree with you 100% there. That was a great question. So another question, Dr. Zanna, you have shown the increasing flood of ocean data that we can use in AI ML, but what data do you not currently have? If you could wave a magic wand, what data improvements would you wish for?
Oh, that's a fabulous question. And of course, it will be kind of a little bit biased, right? So for us in the parameterization world, actually, we don't have a huge flux of observation. We use models still. Because again, getting down to the resolution that you need to capture the processes that we're missing in the climate model, we still don't have enough data, or at least with the data we have not been successful in training parameterization. So for me, much finer scale, process data. So basically, say turbulent mixing and things like this, which we have some, but we're not quite at the stage that we can use them right off the box. That's a brilliant question, definitely.
Okay, another question here about data resolution. So resolution of data is such a large variable. I often see people get very excited about the potential of high resolution data. Obviously, the greater the resolution, the greater the data volume, and often the costs. Given the wide range of user needs, do you have recommendations on appropriate resolution?
Okay, that's a very good question and a tough one again, because as you said, right, so you increase the resolution, you increase the data volume, but for the different processes that we care about, unfortunately, we do need to increase resolution and data volume. The question is, how little can we get away with? I would almost be tempted to say for the AI world, and I think it goes back to my last point, setting up benchmark and test, and it's something we haven't done. So far, with my data set, I say, oh, let's split it in half. And then let's run with that. Do I need more? Do I need less? How little do I need for the process? And that's where the domain knowledge expertise comes about as well, right? Different processes at different time scales and length scale, and you might not need as much. And different methods also require more or less data. Equation discovery, I needed half the amount of data that I needed, say, for deep learning. So different method also face something different. But again, we don't have good benchmarks and tests yet because we're very much at the beginning, and that's something we really need to be careful with. It's a great question again.
Yeah, and I agree. I think in the coastal zone, it's a similar question: is how high resolution do we actually need? Do we need to be down to 1 meter resolution, or is that overkill? I think that's a great question. The next question, in terms of computational resources. So, what types of computational resources and tools do you typically use for your ML work? Cloud, Pangeo, on-prem, HPC. Do you see any opportunities for federal and academic partners to provide compute resources to make AI, ML, and ocean sciences more broadly accessible?
Superb question. So far, we've used everything, literally. So I think everything that was mentioned, Pangeo, cloud, HPC, my own laptop. The first project we did with Tom, my student, it was 2016. We use our laptops. They were definitely, running hot by training CNN, even if it was a very idealized model. We really use that all. Now, how the community should move forward. So I think, Pangeo is a sublime example of how to bring the community together, making the data available and accessible online, being able to actually play with the data directly on the cloud. So I think, a cloud-based shared data set would be absolutely fantastic, right? How feasible it is, coming from the federal agency to support something like this. I think right now, actually, there's a session on open ocean and cloud access that my colleagues in Pangeo actually are running. So I think those would be absolutely fabulous. Being able to share the data set, share knowledge, share our codes, which we already do, but everything is split in different places. And as we said, the amount of data is growing at a pace that is hard to imagine. So if we want to make fast leap forward, so I feel a common base with support would be phenomenal for the field. Also because we can roll out what's not necessary as well, much faster. I also see that as a way to roll out what we don't need.
Yeah, agree with that. And with the OSTP, an AI task force, that seems like they're pursuing some of these things more broadly for AI. So, I would hope that for ocean sciences and environmental sciences, we do the same. Okay, we have time for one more question. I have a bunch of them here. So I'm going to say for this next one, given your background in working with simple models, in quotes there, do you think that they still play a role? In other words, can we learn a relationship with AI ML and then transfer that to a traditional approach? Or does AI ML offer too many benefits that it isn't worth returning to these more simple models?
Very good question. So I've been thinking a lot about this because yes, as you said, I am trained as a, dynamicist that use simple model. I do believe there is a huge value in it. Again, at the end of the day, the point is more not just getting high skill, but can we push the boundary of our understanding so we can make better prediction and act? And I feel for me, this is the way I train my group, is all tools are useful, the old and the new. And I don't think I'm gonna back away from that. I think tools are useful for different problems, and I'm a big fan of all the tools. AI is an additional tool in our bag, the same way idealized models are, and I still use them to explain concept to myself, or when I discover something with AI, to go back. Does that make sense? Or am I learning something new? Or is it impossible? So I'm a big believer in many approaches, many tools. I think that's definitely very important. Very good question.
Yeah, a lot of great questions. So I want to thank everyone. Sorry for the people who didn't get to your questions. I want to thank everyone for joining our session and for asking great questions, and especially thanks Dr. Laure Zanna for the excellent presentation and the discussion. Very worthwhile, and enjoyed it very much. In about 15 minutes, we will start up our next sessions at 2:30. 2 sessions starting then. And Douglas, did you have anything you wanted to add?
Yes, I do have one more slide to share. Like usual, the drill, you all know it. So please join the Slack for the discussion. And I want to highlight tomorrow's plenary session on emerging technology for NOAA missions. We have 3 really highlight talks in the session. That's 11 more in the Mountain Time in the morning. And please join our poster presenters this afternoon at 4 p.m. Mountain Time. There's a lot of great talks, and hope you all will enjoy the poster today. Thank you.